Assalamu alaikum and good day, ladies and gentlemen. I'm Hazima Mosam and I welcome you all to comstech webinar on Hemicalide, a complex marine natural product with strong biological activity. And in this lecture, we are very grateful, will be delivered by Professor Dr. Georges Messiet. We are very grateful for his time and his kind acceptance of our invitation. Hemicalide is a complex marine natural product, and it has, in this lecture, Professor will be elaborating on its structure, synthesis, and its biological activities. With this, I request Dr. Farzana Shaheen from International Center for Chemical and Biological Sciences to please introduce and welcome our guest speaker. Over to you, Dr. Hina and Dr. Farzana.
Thank you very much, Huzema. Assalamu alaikum and good evening to everyone. On behalf of Professor Dr. Muhammad Iqbal Chaudhry, Coordinator General Comstech, I welcome all participants to this webinar on the biological activity of Hemicalide, which is a very complex marine natural product with strong anti-proliferative activity and with a unique mode of action.
Okay.
Many studies on the total synthesis.
Dr. Farzana, I'm sorry to.
Yes.
I'm sorry to interrupt you. I think we have Dr. Iqbal with us. If we can unmute his mic and video, then I think it would be great for us to have him do this honor for us.
We have already unmuted.
Okay, thank you, Hazima. Thank you, Dr. Hina. Thank you, Professor Farzana. And thank you, my dear friend, Professor Dr. George Messiet, someone of my very close associate since last 4 decades, and I have a lot of respect for him. I am traveling to Ankara in Turkey, and I'm in the ambassador's house at this point, and I'm very pleased that despite this mobility constraint, I would be able to see the lecture and to introduce you to a very fine chemist of very high caliber. Professor Georges Messiet is known to us since last several decades, and his chemistry is of a very high quality. So I would let Dr. Farzana introduce Dr. Messiet, but let me tell something very important about him to the audience. Audience are from different countries, and comstech being the second largest group of countries in the world, both in terms of number of member states as well as OIC institution, which comstech is a very important organization of OIC, Organization of Islamic Cooperation, and we have audience from different countries. George is unique in many sense. Perhaps the most important one is that his chemistry is extremely interesting, multifaceted, and also very innovative. He has been a learner of chemistry because he's changing and very shrewdly from one thing to the other, keeping the excellence of chemistry alive. Second important thing is that he is a very universal person because he keeps working with scholars from all around the world. And he has this tremendous track record of helping people from different countries. So he has not only kept his chemistry to his own country, to his own people, but in fact spread this knowledge all over. Third is that he has been helping countries like ours in Pakistan and other places in developing capacity, and one proof of it that he was a member of a very important committee which selected the International Center for Chemical and Biological Sciences as the center of excellence in the field of chemical sciences. And he has since then supporting our institution, our scholars, and helping them to develop their capacities in different fields other than chemistry. And of course, the fourth most important thing is that he has been a close friend. We have a good understanding. And despite the fact that we haven't really met since last 2 years, we are eagerly looking forward to meet him as soon as possible. So George is certainly one very high caliber speaker, and Comstech is very proud to have him on board, very proud to benefit from his knowledge. Certainly one of you will benefit from his tremendous experience in the field of natural product and also in synthetic chemistry. Thank you very much.
Thank you, sir. As Dr. Saab has said that already introduced, and I will just add a few more, some of his achievement now. He has many publications on the synthesis and structural studies of complex marine natural product Hemicalide. In this webinar, this is a great honor for me to introduce Professor Dr. George Matthew. Professor Dr. George is Emeritus Research Director at the University de Reims, and he has completed his PhD from the Institute of Chemistry and Natural Substances under the direction of Professor Dr. Henry Philip. He did his postdoctoral studies at the University of Wisconsin Medicine under Professor Barry Trost, and then he got CNRS position from 1977 to 1998 at the Faculty of Pharmacy, Reims. He worked as Deputy Director of CNRS Department of Chemical Sciences from 1992 to 1998, and then Director of Natural Product Research Center from 1998 to 2010. And since 2013, he is Emeritus Research Director at the University of Reims. Professor George is working on a number of fascinating natural products, especially on the examples of natural product structures that remain to be solved for the development of new drugs. His field of interest are on natural products, separation, structural elucidation, nuclear magnetic resonance studies, partial and total synthesis of many classes of natural products, including alkaloids, terpenes, saponins, and sugars. Professor George is author and co-author of 268 scientific publications. He has 5 patents and 5 book chapters, and he has produced 15 PhDs. The recent publication of Professor George is also based on the investigation on the assembly of the entire carbon backbone of a stereoisomer of anti-tumor marine natural product Hemicalide. We are very grateful to Professor George for his time and for accepting this invitation to deliver his talk on this very important topic of biological activity and structural studies of Hemicalide. Now I welcome Professor George for his talk. Thank you.
Thank you, Ina. Thank you, Kasima, for arranging this thing, and thank you, Iqbal, for the kind words of introduction that you gave. I'm actually thankful to you to give me the opportunity to talk about this project. I say project because it's still alive and people are still working on this molecule. It's not finished. And it's a very particular thing because the discovery of this molecule was done in the framework of a industry and agencies partnership, private industry and private partnership. So it's particular because we never published on this molecule. And I am grateful to you to give the opportunity to gather a few slides on that, because since like I say, we haven't published, and that gives me the opportunity to review all the data we have. And I'm sure that just after this lecture, I will start again writing about this compound, the full paper. So I'm going to introduce the marine natural product and say a few words about their usefulness as drugs lead in the pharma industry. Then I will give you some overviews of the structural elucidation of this complex molecule, as well as the beginning of the synthesis work that has been done on that. So what is known, what is publicly known about this molecule is this patent. We filed the patent in 2010. The patent has been filed in the USA, in Europe, in Japan, and it contains the molecule. Okay, it contains the structure of the molecule, and what is protected is this molecule as well as the diester isomers. And if you can count, there are 21 asymmetric centers, so it's more than 2 million isomers. We also patented the salt, since it's an acid, and we have patented esters of that. So this is what is publicly known. So let me tell you why we went into this business. I'm sorry, it goes slowly to switch. Okay. Okay. What is the key word in the research of drug leads is the diversity of structure that you can have. The activity is something I would set aside. We suppose that industry is working on active molecule. It's not always the case, but in our case, that was what we were looking for. And diversity in the sea, in the ocean, is little explored. And it's very wide diversity. Why is it so wide? Because life started in the ocean. And what we have on Earth is what is able to survive in the oxygen era. So there is probably more life under the water than above the water. Translated into chemistry, I mean that the chemodiversity is larger in the ocean than on Earth. The marine molecules have a particular feature, is that they're usually more powerful than the terrestrial molecules. And there is a simple reason why. If a sponge or an organism makes a molecule, it's going to be immediately diluted in the water, in the ocean. So because of the dilution effect, this molecule should be very, very potent. And this is the case. Also, why industry is interested in the ocean, it's because they are not subject to convention on biodiversity. That's a minor point, but it's a major point for industry. There are inconveniences in working with the ocean. First, it's not easy to count the resource. If you're looking for a tree or for a plant, you can count them on a certain amount of land. You can imagine how much there is. Under the ocean, no way. You can see sponges at one point, but you don't know where the other ones are. So one of the difficulties is to secure the second collection. Second collection is the word that we have in the industry. I say we because I have been part of the industry for 15 years. Second collection is the collection that you made once the first one proved to be useful. So one of the solutions to that second collection is the cultivation of the organism, not the harvesting. Also, you must keep in mind that synthesis must be an alternative source, even though the molecules are complicated. I'll give you some example of molecules from the sea. Toxins from the sea are very well known. On the left, you can see a red tide, and the red tide is due to a dinoflagellates, which makes saxitoxin, this molecule that you see in the middle of the screen. Saxitoxin is very, very toxic. But industry at one time was interested in this molecule in the anesthetics era. If you can make people sleep for 24 hours, that's useful. There is actually no drug for very long-term anesthetics. The one nearby is tetrodotoxin. Tetrodotoxin comes from a fish, the fugu, and it's a delicacy in Japan. They like to eat the fish, but the fish must be cut properly, otherwise you get the tetrodotoxin, and tetrodotoxin can kill people. Actually, low doses of tetrodotoxin are probably involved in the process of what I would call zombification. This is a practice done in the islands in the Caribbean, where some people are made like if you are dead because they inject tetrodotoxin, but in fact they are not dead and they survive, but like zombies. That's one of the features of tetrodotoxin. Some other molecules, the brevetoxin, polytoxin actually is believed to be the most complex organic molecule made in nature. And it has been made by synthesis. That's usually what is called the Everest of synthesis. I'm happy to show gyroline because they are not always large molecules. They could be small. Gyroline is an imidazole discovered by Pierre Potier, whom you know, certainly some of you know, and it's a powerful cytotoxic. Drugs from the sea. Actually, people claim that cytarabine and vidarabine, which are nucleosides, were isolated from sponges, and they are. But the molecules which are marketed as anti-cancer drugs are not coming from the sea anymore. They are made by inspiration from this molecule. One of the first molecules to reach the market is yondelis. It's called ET743 trabectedin. It's produced by a Spanish pharmaceutical company, and it has been approved for some solid cancer treatment in 2007. Actually, it's made by partial synthesis from a microorganism. You have the structure on the right. It's not a very complicated one. It has been made several times by total synthesis, but now the core of the molecule is made by a microorganism. It's not a big molecule as far as market is concerned. A more interesting one is eribulin that you see on the right side of the molecule. And it's inspired from alicondrin. Alicondrin is a very complex molecule isolated in the 80s by a Japanese group. You can see the figures like 12 milligrams from 600 kilograms of sponge. I suppose it's white sponge, but still it's very rare. Synthesis was made, even though it's a complicated molecule, but that was just the beginning of another story because the group of Kishi at Harvard started to make simpler molecules inspired by alicondrin. And they discovered that the left part of the molecule is not useful for the activity. And they made many compounds. And the one which has reached the market is eribulin, named Alaven. And it's used in cancer chemotherapy. And it is sold, I would say, almost $1 billion a year. It's made by Eisai, a Japanese company. And the synthesis is something like 35 steps. This is about the limit that synthesis can be done in the industry. Next. Okay, so at Pierre Fabre, which is a medium-sized pharmaceutical company, we were interested in cancer. So what is cancer? It's an anarchic proliferation of cells. And in the process of proliferation, we target the mitosis, which is the mechanism of cell duplication. So we look for mitotic blockers, and we devise a high-throughput screening assay based on an antibody which recognizes phosphorylated proteins accumulated during mitosis. Then you have an ELISA test to detect the recognition. This assay was applied on our collection of drugs and of extract. And we were glad to find the vinca alkaloid, taxol, podophyllitoxin, colchicine, cobotastatin. They all came out from this assay. But we had a good and original hit from this little sponge that you see, the orange stuff, called Hemicalide from Vanuatu. And that's the beginning of the story. So where is Vanuatu? Vanuatu is near Australia. It's a set of islands. And on this map, you can see the route that the boat followed. The boat was coming from the French New Caledonia, headed north, and the collection was made in the two archipelagos, which are on top, the Torres and the Banks Islands. It was not an easy collection because the sponge was collected at a depth of, let's say, 50 meters deep, which is not easy diving. I mean, the divers were allowed to collect during 20 minutes, no more. And then they had to readjust to the pressure. So it was difficult. And we managed to have the sponge collected by the kilogram, but no more, just the kilo twice. And then chemists came into scene. And this is what I would call a tedious separation. I mean, it was really painful because the extracts were complex, but after a while, we were able to concentrate the activity into a single peak. You can see the HPLC on the right. The UV showed an extended chromophore. It went to 306 nanometer, and the mass spec was above 1000, corresponding to a formula with 59 carbon atoms and 16 oxygen. So sort of a complex molecule. Meanwhile, we've been busy looking at the bioactivity. Remember, that was done in the framework of an industrial partnerships, and they were interested in active compound. So what was noticed for this molecule is that a 5 to the 10⁻⁸, the centrosome was deprived of tubulin alpha and beta. But the molecule does not act on isolated tubulins alpha and beta. And we think it acts on the interaction of these tubulins with tubulin gamma at the centrosome, which is a really exceptional observation. We didn't have any reference compound with this activity. And this is really what the pharmaceutical industry is looking for. We don't need cytotoxic for themselves. We need different cytotoxic, and that was a different one. The cytotoxicity was very high, and you can see on the lines below that it went to 10 to the -10, so picomolar. And there is a range of activity depending on the cell from 10 to the -9 to 10 to the -11. So it's 100 of difference between those two. So there's some sort of selectivity. The first thing that a chemist would do with a molecule once he had the UV, he had the HPLC track and a mass spec is put that into adenoid tubes. And this is what we had. Compounds look reasonably clean. It shows that it's a complex molecule. It shows double bond. It shows methoxy, and it shows a lot of muscle group bound to carbon. That's the beginning of the story. So I'm not going to tell you how we proceed to obtain the structure, because believe me, it took us 2 years with 2 persons, me and another lady, being fully in charge of that. I mean, with all the data in our minds and all the time trying to advance, move, make proposals, and really took us 2 years to have a satisfactory answer. The main tool that we have used, first, just give a look at an expansion of the olefinic proton. And very rapidly, we can tell that there were 3 elements, a triene, sorry for that, a triene, all conjugated, all trans, which is responsible for the UV we've seen. Then we had protons from a diene and a trans isolated double bond. I mean, isolated in the middle of nowhere, there was a trans double bond. So these were only the features that we could obtain just by looking at the spectrum. Of course, we did more than looking. We did some further experiment. What I would like to say right now is that a triene like that with an acid function is a rare functionality. So that was the first proof that we had something special in our hands. So the main tools that we have used to unravel the structure is to look at the HMBC correlation. The HMBC done on the methyl group gives you a lot of information. From this methyl, you can have these 3 carbon being observable. And if one of these is on a double bond like this one, you can see it. If there is an oxygen beta, you can see it. Also, from the methoxy, lower methoxy, you can see the carbon on which they are attacked. It is not the first experiment that chemists do the HMBC. Usually you start with the COSY, and I will show you later that the COSY is complementary. So this is the structure. Like I say, I'm not going to make the demonstration, but I'm going to show you how useful are the techniques. So the methyl doublet that we are looking at, here they are. There are 9 of them. And if we believe in the HMBC, in red at the bottom, you can see that you can, in principle, have the 2/3 of the molecule seen from that single experiment. I'm sorry, it takes time to change slides. Okay. Okay, this is the HMBC, an expansion of the HMBC on the famous methyl doublet. You can see that there are 9 of them. There are 4 on this side and 5 on this side with an overlap of 2 here. And here you see some sharper lines, and those sharper lines are coming from, it's a triplet, an impurity, probably some ethanol present in the methanol. And you can tell it's not from the molecule because the width of the lines is sharper. So well, what do we see? What do we see? On each line of the methyl, you can see 3 correlations, 3 here, 3 here, 3, 3, except here. Here you have only 2 correlations. That means that we have a CH3 terminal. And if you look at the beta carbon is in the 70 to 80 ppm range. That means, sorry, it means that there is an oxygen behind it. So we have a CH3 CHO, which is the first element that we can get from this experiment. Then you can see that there are some methyl, actually 3 of them, which see double bonds, since we are here in the 120, 130 ppm range. And most of them, most of them correlate to oxygen atoms. There is one in there which does not have a correlation with no correlation with an oxygen atom behind. So I say that the COSY should bring some experiment. Again, you can see the CH3 doublets, and actually the CH to which they are coupled, most of them are buried in this region, which I would say the fat region of the, and it's not very useful. But 4 of them are distinct. One coupled to a proton at almost 4 ppm. That's the famous CHO that I spoke about. And there are 3 which are here different. And it means this is allelic protons which are there. And this information we had before from the HMBC, just these are the 3 correlation with the double bonds. So just to show you that you can see something with the COSY experiment. Sorry, it takes time to switch slides, but I cannot go faster. I'm trying. No, okay, so these are the kind of linkage that you can see on the HMBC. For example, if you look at this muscle, which I number 3 because it's the 3rd one, you can see that it couples to both a double bond and to an oxygen-bearing carbon. Let's say this is this muscle coupling to a double bond on one side and an oxygen. And these oxygens that you can see here is seen by the number 9, which is here. And the number 9 see another oxygen-bearing carbon here, which can be seen by number 7. So if you look at this experiment, you can deduce that you have this chain of 3, contiguous CH through CH separated by oxygen-bearing carbons. So we have 3 of them. So this is the way we have used this HMBC experiment to bring larger elements of structure. I'm sorry, again, it goes slow. Bah, c'est ça là-dessus qu'il y a plus. Okay. HMBC has been used also to localize the methoxy. Like I said, the 3 methyl group that we have in the molecule, this big is the solvent, gives a correlation to CH in the 80 ppm range, which is normal. One of these, methoxy, and only one of these couples in the area of the methyl group, which are here. And this is the reason why we decided that this would be this one. And the couplings that you see, this carbon atom, are those on each side. So you have 2 methyl group, which is this methoxy. And that allows to refine the structure and place the methoxy group on the side of the double bond. Those 2 methyl have no link whatsoever with this CH3H3 area. So that means they're somewhere else on the structure. Okay, it goes faster. So we can also see the methyl group have some more information. The methyl group that see double bonds. So number 3 that we have seen, and number 4 couple with double bond. And you can see here on the same in the same experiment, these HMBC and HSQC, what it gives, and that allows you to detect this muscle, which speaks to this doublet here. Here you have a doublet, since there is only one here. And here we are in the trans double bond. The trans double bond is here, so a muscle sees it. So this is a little bit more, which can be seen from this experiment. Can we assign all these muscle? Yes, we can. We've seen how to assign these 3 ones there. Then we have seen this one. It's more difficult to see this one and this one because they are in the middle of nowhere. This one is the one which coupled to no oxygen atom at all. There is nothing, just middle of nowhere. And what is very interesting in this experiment, if you count the number of oxygenated carbon atom you find 13, which is exactly what you should find in this molecule. So it's possible with the COSY and a lot of patients to assign that. We can do the same experiment with the muscle singlet. So there are two muscle. They are not really singlet. They are broad singlet like muscle on double bonds. There are two of them. And it's possible to see one of them as a correlation with this oxygen-bearing carbon there, which is correspond to methyl number 7. And the other one not, but the other one can be linked differently. It's also sort of easy from the double bonds to see the allelic proton, and we have the allelic proton, and with a simple COSY, we can assign them. And we can see that unfortunately, all the allelic proton, which are here or here or here, they are in this area which is not structured. I mean, there is all the protons are together, and it's not very easy. You can see the two muscle correlation here. That's long-range coupling between the muscle and the allelic and the muscle. So, I mean, all the methyl can be assigned with this experiment. Finally, an experiment which we use at the end, it's a difficult to use experiment, it's the TOCSY, total correlation spectroscopy. Some people call that also OHA. That's only part of the OHA. From one methyl, for example, you can see the proton which couple to the proton, which couple to the proton, which to the proton. For example, on this line, you can see all the double bonds coupling to this methyl group, which is here, somewhere here. So with this experiment, just looking in the area of the muscle, we are able to distinguish 4 sets of or line, a large line corresponding to this part, and then a line here corresponding to this double bond area. And in fact, you see it here, but you see it here, it's the same. And then you can see this one from this small part, and you can see the end because we know the terminal muscle. So these are parts of all the elements that we have to keep in mind to be able to assemble a full structure. So to make a long story short, what have we been able to assemble? We have, we had these long molecules. We had this part with not much information. That's the end of the molecule. And these are tiny bits, the double bond here. And it really took us a while to assemble that in a satisfying fashion. And I see 5 fragments and 2 silent art. Silent art refers to a terminology that was used by Woodward when they were looking at the structure of strychnine. Strychnine, they could get information of all the atoms which were on the outside of the molecule, but the art was silent. It's the same for us. Very little information of that. Of course, we knew this proton, we knew this proton. Of course, we knew this and we knew that, but it took us a while to dare assemble that. And at the end, it gave us 2 possible formula, one with 2 lactones together and a linear one. I mean, in fact, the molecule has 2 lactones here, or here or here. These are the same, they are isomers. But this one was preferred because at that stage, we introduced other data such as NOEs. We had NOEs also. So that was the end of the first part of the story. And we were able to admire this molecule, which is unique. Like I said before, the triene, this is almost unique. There are some triene like that in literature, but not that many. But the lactone, believe me, this one or this one, they are not to be seen anywhere. I mean, a few years ago when I was looking at the literature, but I don't have seen that before. So it's beautiful because it's complex. It has a very, very powerful mode of action. It should be a nightmare for synthetic chemists and the beginning of the story. And we have started. From that point, the industrial partners say, okay, if you can make it, but I will disengage. But we were engaged with the CNRS, which is a civil institution, and they decided to support research on that, and they support several theses. And we had one student who started, sorry for that, who dared to start the synthesis. And we started from the acid side, see if we can get the relative stereochemistry around this, all these centers. So the first thing they did is they did an extension of some rules proposed by Kishi. Kishi is the chemist who made polytoxin, and he also worked a lot of polycated of this kind, and he devised a rule to determine the configuration of 2 units like that. I mean, 2 units like that, maybe 4 asymmetric center. So we propose to extend this rule to exates. That means 3 units. And we got rules, but they didn't work in our case because there were perturbations because of this methoxy. The Kishi's rule do not have methoxy, and the simple methoxy changes everything. But what we did is we noticed that we had a carbon atom resonating at 7 ppm, which was upfield. It's the only one in this part of the spectrum. All the other ones are above 10 or equal to 20. And there was one at 7. And the only relative configuration which accommodate that is a null sin configuration. So that makes the problems a little bit simpler. So we just had to make these 6 diastereoisomers of these molecules to figure out which was the good one. And the students did that. The way we did that is to do a Woodward-Simmons olefination. That means it's a sort of a Wittig reaction in this side. You must have an aldehyde and a phosphonate. Suzuki coupling, an aldol compensation on this side. The way this triene was made is very clever, and that was devised by Professor Cosi, which was a partner in the business. This is sorbic acid. Sorbic acid is not a rare molecule. You can get it by grams for cheap. And what she found out is that you can do a simple metathesis of this molecule with the allyl bromide corresponding to that to exchange that for a beer. I mean, all chemists like me would have performed a bromination, which would have given a mess. But the metathesis give really right away the bromine here and then the phosphonate. This part of the molecules come from very clever chemistry. It's tough because it starts with T-butyl lithium, which we don't like to use. And you can open that and make this. And the difficulty is really to make the middle. And of course, it's in the middle that there is the asymmetry. All this chemistry is known. It's known from an English professor named Jan Patterson, who has been working on that for years. And as a matter of fact, Patterson rapidly noticed that there was that molecule named Hemicalide, and he has also embarked in the total synthesis of that. But we've been using his tools. So that starts from an ester, which is named the Roche ester. The Roche, it's the name of the pharmaceutical company. The Roche ester is available in both enantiomeric form, and you can easily transform this ester into an aldehyde, or you can make an ethyl ketone on that. And the condensation of that, depending of if you make the E or Z enolate of that, you can make vary the all the asymmetric centers there. And this is how we made this molecule. And from this one, we use some of Evans chemistry. So this is another, that's an American one. Is using these chiral staff, chiral auxiliary to make chiral enolates, and those chiral enolates react properly with aldehyde. And this is the way we made this this amide, and from this amide we made all these isomers of that. And then what we had simply to do is to look at this molecule and compare to our molecule. So there were 6 molecules which were made. So the sequence was run 6 times. One of the isomers gave a better fit, but the fits was not ideal at all. And that's when we discovered that, in fact, our natural product was not an acid, it was a salt of the acid. And if some of you are interested into looking at salt of natural product, marine natural product, I encourage them to go to this publication by Proton. It's a review article, and it's based on the fact that these large molecules from marine origin might be chelators of ions. And it's probably the reason why they are so complex, because they want to really retain strongly some metals. And I'm afraid this is what happens. So as soon as we had published that, we were joined by an article by Jonathan Goodman from Oxford, who's the person who does calculation of carbon-13 NMR spectra. And among maybe 20 examples of molecules that he described, there was our molecules in the middle. He found it, and he agreed with our proposal. He's still competing after us, and he joined Patterson on the total synthesis of the rest. So just to finish and give you a hint of what is behind us, we try to make the lactones. You see, like I said, they are unusual lactones. First, we focused on this one. This one might look more complicated, but we were pretty sure that the 2 hydroxyl were synced to each other. So a double bond, like here, would be a means to introduce that. And the way the person who did the synthesis, this is the group of Jenny Gardison in Paris, how they make that is to use a metathesis. So this is an example of a metathesis to make a lactone. This is also some originality found in this project. So simply what they had to do, sorry again, simply what they had to do is to do these molecules. In fact, there are 32 isomers. They were not all done, but we made many of them. And the catalyst we were used to do that was not the original catalyst, not the group's catalyst, but the Nolan catalyst, give like 80% yield of the lactone. Then the oxygenation was done with a variant of the osmolation reaction, and we were able to make these as well as isomers and compare that. At that stage, there is still a controversy between our result and those of Patterson, because Patterson is on our back and he does not agree with the configuration of this method with regard to that, which is a difficult point. And he made the differences are tiny, but he claims there are differences. The second and last lactone was done differently. I say it's simpler lactone, but there are more isomers, 64. And it was decided that was done by Janine Cossy, whom I mentioned earlier for the triene synthesis. And they use a conjugate addition on a preformed lactone. So if you have this lactone with these two asymmetric centers, say, you can enter a vinyl, it's a boronyl derivative, a boron derivative that does conjugated. And I was afraid of that reaction, but it works. They make the anions and were able to oxidize the anion, which is not the usual way to make that, but they got decent yield of this molecule and the right stereochemistry. So they made 3 isomers, and they found out that this one was the most probable. Configuration at this stage is far from being certain. So finally, a single lady, I want to mention her name, it's Camille Lecour, decided to go for the full synthesis. When we embarked on the synthesis, there were 2 groups working on that. One was working on this part and one was working on this part. And I thought they would join somewhere around there. That's not what happened. What happens is that the lady working on this side pushed and pushed and pushed and finally managed to make everything from these 5 building blocks. And in 2019, they were able to produce the first isomers of the molecule. Is that the end of the story? No. We found a beautiful and interesting molecule. The structure is yet to be fully determined. We know that Mr. Patterson is advancing on the structure, and I'm pretty sure that it will finish at least one isomer. See, the difficulty is in the part that I call the silent art, the part with the 2 metals. That is going to be very tough to determine which they are. But these guys are doing a lot of calculation, ab initio calculation, if they believe it works. So one of the questions we ask ourselves from the beginning, was it worth isolating molecule from sponge? I would say yes, because we wouldn't have found the molecules without doing the isolation work. Because some people claim that sponges are hotel from bacteria, and it suffices to isolate the bacteria, cultivate them to find the right compound. We tried that. We tried that. On the second collection of the molecule of the sponge, right on the boat, we had someone looking at bacteriology who had secured some samples for cultivation. And indeed, they were able, to isolate something like 160 different bacteria. Some showed some activity, but so far, we were not able to find the molecule from these bacteria. Probably the condition of production of these molecules are very, very sharp. And we did the cultivation on the sponge itself, but probably we were missing some of the parameters for the cultivation. And it may take still a long time before we find this molecule, unless the biology, I mean, the sequencing of the genomes of all these bacteria give us the solution. So before finishing, let me acknowledge all the work of the people who took part in that. The collection was done by a lady from the Institute of Research for Development in France, Cécile Debitus. She was a diver. She still is a diver. Actually, I understand that she has retired recently and she's living on a boat across from Brittany. And the boat who who carried the divers was named the Alice. The isolation work was performed by a single person, Isabelle Carletti from Prof. She did a fantastic work isolating that. That was not easy because, believe it or not, there were also molecules of less interest in the mixture. High-throughput screening was done by Frédéric Ossey and his team from Prof. The valuable observation of microscopy was done by Dr. Michel Wright, who is a scientist from the senior race. Structural elucidation was based on the work of Laurence Marcourt, and I say myself, but I'm not going to acknowledge myself. So we did that together. I don't know who first wrote the first formula, but it was one of the two. We're not going to fight for that. Microbiology was done by Philippe Le Baron at Banyuls, which is a laboratory from the Paris University, which is by the sea. And there are the two groups of synthesis. The team one who started the synthesis was done by Yannick Hardisson and Ange Pancroisi, who unfortunately passed away during the work. And there was another team in the School of Chemistry, not far away from that, directed by Janine Cossy and Christophe Meyer. There are three students that took part in that for the thesis. I really want to mention their name. Etienne Fleury is the one who dare go into this business first. He was a very bright student. What he says is very important. We're confident that the configuration he determined are good. He's now working from the Michelin tire. I don't know what he's doing with Michelin tire, looking at material, but very good student. Simon Specklin, now who works for the CAA, Center of Atomic Energy in France, did all the right part of the molecule. And Camille Lecourt, she's a lady, she assembled everything. I don't think she invented the reaction, but she managed to run the sequence all across. And funding institution was Pierre Fabre, the laboratory. IRD would provided the means to go to the sea, do the correction, and so on. CNRS took part in many aspects of this research at many places. I'd say it was a joint venture between CNRS and Pierre Fabre, this story, and the National Agency for Research provided funds for the last students. For those who are interested, we never published the structure yet, but we published quite a few papers on the advancement of the synthesis. And yeah, this is the latest paper. And of course, if you want to compare, just type Hemicalide on the website and you'll find the papers from the English groups, which is really on our ears. I would like to thank you for your patience and attention. One of the this webinar is that I can see that we are more numerous at the end than at the beginning. So thank you all for your patience.
Thank you so much, sir, for such an informative, excellent lecture. We all learn a lot. I'm sure it is benefiting students as well. I see lots of appreciation in the chat box, and I have a few questions. If you allow, may I kindly read them for you, sir? Okay. The first one is, thank you, Prof, for your presentation. Question is the level of purification of this class of compound. Have you already developed method for their isolation using HPLC in your research group?
Oh, yes, it is. Of course, this is HPLC. One of the easy things with this molecule is that you can see the chromophore. It is a molecule that you can see. Of course, we did a lot of HPLC for that, the reverse phase HPLC.
Right. Okay, there is another question. The molecule have lots of stereo center. Did you get single stereo isomer? If not, so how much reliable of the activities of these compounds are?
This is a really tough question. I mean, we've did some preliminary investigation on some of the intermediate, and what we wanted to find out if there was a little bit of activity in one of the intermediates. And so far, it is not conclusive. We don't have found anything. So what we would like very much to do now is simplify the molecules, make it simpler, and try to find the activity again on simpler model of that. And I believe that will work. Will we ever find the right stereochemistry? I don't know. One of the reasons why we never publish is that we don't have full data on the molecule. For example, I don't have a rotation. If you ask me what is the rotation, I would say it's probably -5 or +5 or whatever. It's not being significant. But for many journals, you need to have a rotation. Why don't we have such data? I don't have an infrared either. It's because it was done, like I say, in the industry. And to continue the project, we must show that the molecule was active. So most of the molecule was burned by the biologist, and we don't have it anymore.
Okay, great. Thank you, sir. Rest, I see lots of appreciation and thanks to you from the audience. Certainly, it was very exciting lecture. And on behalf of everyone, the audience, organizers, I would like to thank you. And you see, the house is still full. We have 94 participants attending and listening your lecture. So much appreciated. Maham, would you like to add something from Comstech?
Yes, thank you everyone for joining us today. Thank you, madam. Thank you, Professor Georges, for this wonderful and informative lecture. I would like to inform everybody that you will get your certificates after 7 to 10 working days. And thank you so much for joining us today. Thank you.
Okay. Looking forward to see you in person, sir.
I hope so. I hope so.
Yeah. Okay. Thank you, everyone. Bye-bye. You all have a good day.
Thank you. Bye-bye.